Okay, so for the next example, we are going to do CCl2 minus 2. So for this structure, we need to draw the Lewis structure, which means we need to determine the total number of valence electrons in the molecule. So for carbon, there is one of them, and carbon is in group 4, so it provides 4 valence electrons to the structure. For the chlorines, we have 2 of them, and chlorine is in group 7, so that provides us with 14 of the valence electrons. Now, for this molecule, we also have a charge, and since it is a minus charge, that means we need to add electrons. And since it is minus 2, we need to add 2 additional electrons, giving us a total of 20 valence electrons. So, we determine our skeletal structure. What is our central atom? We know that it's carbon, and it is surrounded by the 2 chlorine atoms. So we've determined the skeletal structure. Now we draw a single bond from our central atom to our terminal atom. So single bond. Then for the fourth step, we give our terminal atoms an octet. And chlorine is not an exception to the octet rule, so we know we have to draw it with 8 valence electrons. There's already 2 drawn from the bond, so I draw 6 more valence electrons around the chlorines. So then I look, how many of the 20 have I already drawn? And I see that I've used 16 of them. So I know that when I've given my terminal atoms an octet and I have any of the total valence electrons left over, I put them on the central atom as lone pairs. So in this case, I've used 16. There's 4 electrons left over. So I draw them on the central atom as lone pairs. So I see that I've used all 20 of my valence electrons. My chlorines have an octet, and if I look at my carbon, I see that it too has 8 valence electrons, so it has an octet. So I know that this is the correct Lewis structure for this particular molecule. However, remember that when you have a charged species, you need to include brackets and charge around the molecule for the Lewis structure. Okay, so for the 3D molecule, we look at the central atom and we see that there are 4 regions of electron density around the carbon. Now that narrows it down. Again, we have one of 3 possibilities. We can either be tetrahedral, we can be trigonal pyramidal, or we can be bent. Now if I look at the type, I know that I have 2 bonding pairs from the bonds from the carbon to the chlorine, and I have 2 lone pairs on my central atom, giving me a total of 4 regions. So when that happens, when I have this combination of electron density around the central atom, I know that it has a bent geometry. Now, I know that any molecule with 4 regions around the central atom is going to have the overall bonding structure like this. Now, for this particular molecule, we would have carbon, 2 bonds in plane, 1 coming out, 1 going behind. So regardless of what type, we know that if you have 4 regions, this is the general structure that you're going to see when you generate the 3D molecule. Now, if we look at this structure, we know that all of these bonds are equivalent to each other, meaning it does not matter where you place the lone pairs. So I'll put 1 lone pair here and 1 here, and then put my chlorine in the remaining spots. However, if you put them in any combination of the other bonds, because all 4 of these bonds are equivalent to each other, it would still be considered the same structure. So if we look at this molecule, we see that we have our 2 lone pairs, we have our 2 chlorines there. Now, the experiment itself does not ask, but what would be the polarity of this molecule? Would this be a polar molecule or a nonpolar molecule? So, we have to determine, do I have a net dipole moment? And if I look at this structure, I see, well, I know I have polar bonds. And you know, when you have polar bonds, it can either be a polar molecule or a non-polar molecule. So you have to ask yourself, do I have a net dipole moment? And remember, it's not always easy to determine that, so I gave you those little tips to determine whether or not your molecule is polar or not, meaning does it have a net dipole moment. So the first question you ask yourself is are there any lone pairs on the central atom? And what you see in this particular instance that yes, there are. In fact, there are 2 lone pairs. And as a result of that, because there are lone pairs, you automatically have a polar molecule.